everybody. I'm David Porfirio, and today I'm going to talk about the work that I did with my colleagues, Evan Fisher, Allison Sauppé, Albarghouthi, and Bilge Mutlu, which we've titled Bodystorming Human-Robot Interactions. I'd like to begin by giving an overview of the culmination of our work, or the end product, if you will. So we've created a design tool called Synthé that records designers as they act out interactions between a human and a robot, and results in a full interaction program that can be run on a real robot. In discussing this project in more detail, I'll start by talking a bit about the background of the problem that we're trying to solve and our research question, followed by talking in more depth about the design interface that we've created, which again is called Synthé, and then discussing what's under the hood of the interface, or how specifically we go from designer demonstrations to a fully articulated executable program. And finally, I'll end the talk with a discussion about our evaluation of Synthé. So I will begin with the background. So what is an interaction program? For our purposes, it is a program that tells a robot how to interact with a human. So for instance, we can visualize an example of such a program as a state machine, in which the robot might wait for the human to acknowledge it, followed by greeting the human, making a delivery, and then saying goodbye, and then answering any questions that the human has during the process. Now, this program must be implemented on the robot in some way, and regardless of how implementation occurs, this process traditionally occurs through some programmer or designer coding in front of a screen. Using this method, the designer will face a number of challenges, though. The designer must come up with ideas about how the robot should behave, all the while being focused on how to implement these behaviors onto an actual robot. For instance, the designer has to imagine what social cues would be best to use on the robot, which could include verbal cues and gestural cues, and they must figure out how the robot should repair breakdowns in the interaction, such as if the end user becomes frustrated with the robot. All of this must occur while the designer ensures that the program is implemented correctly, and while being concerned with the syntax of whatever programming language they are using. In the extreme case, the designer might not even know how to code. So these implementation challenges can be a distraction from pure ideation, which in other words is focusing purely on what the robot should do. Proper ideation, uninhibited by implementation, is our goal here. And I want to talk a little bit more about ideation. There exist many methods to ideate designs for both experts and novices that all get at the same idea. We can know more than we can tell. Or, in our case, we have this intuitive or tacit knowledge of social interactions that is difficult to express in words and difficult to express in code. One such design process that embodies this idea is called bodystorming. And bodystorming traditionally involves role-playing, which in our case could mean that one designer acts as a robot and another designer acts as a human end user. Bodystorming also involves environmental similarity, which refers to brainstorming in an environment that is similar to the environment being designed for, and is often achieved through the use of props. With bodystorming, we can unlock our intuitive knowledge of social interactions to form ideas about how we should program our robots, uninhibited by implementation. However, we still need to reconcile ideation with implementation. So our specific research question is, how can we enable design teams to leverage their intuitive knowledge of social interactions to prototype human-robot interaction programs? And our proposed solution is twofold. Firstly, we propose to capture designer intent as design teams bodystorm a human-robot interaction program. And secondly, using observations of designer demonstrations, we propose to synthesize a full human-robot interaction program. What this solution will allow us to achieve is enhancing designer ideation while removing the distractions that come from implementation. So now I'll talk in more depth about the design interface that we created, which again is called Synthé, as a way to achieve this solution. This is our tool, Synthé. At its core, Synthé directly enables designers to perform three tasks. The first, acting out interactions while Synthé records them. Synthé will then generalize the recordings to a full-blown interaction program. The second is editing the recordings using a graphical interface. And finally, the third is simulating the full-blown interaction program on a real robot. Let's first go over the acting component. So in this video, two designers demonstrate or act out examples of how an interaction should play out between a human and a robot. Synth is recording them in the background, using microphones to capture speech and armbands to capture designer gestures. The speech and the gesture streams are labeled and overlaid with each other in order to create what we call a trace, which is short for execution trace. A trace simply contains the sequence of events within a demonstration that designers have provided to Synth. The states are annotated with the robot actor's speech and also the gestures that the robot actor performed. The arrows are annotated with the end user actor's speech. After performing a demonstration, the trace will be presented to designers to either accept or reject, and the trace will be used as input into our synthesis algorithm, which generalizes all traces previously seen into a full interaction program. And we represent these programs as finite automata. Zooming into part of the program on the screen, we can see how this automata works. The automata is actually considered to be what is called a mealy automata, in which branching only occurs at unmarked states, which are represented by circles. These circles represent the decision nodes that the robot must take. Arrows leading away from the decision nodes represent actions that the end user takes. And finally, boxes represent actions performed by the robot in response to an action taken by the user. So back to our three functions. I'm going to now briefly give some details about the editing component of Synth. Again, after performing a demonstration, the trace will be presented to designers to either accept or reject. Designers can edit the speech associated with this trace. Also, they can edit the speech categories and the gestures that have been captured through their demonstration. And once designers are happy with the set of traces that they've provided to Synth, they can activate their program and simulate it on a real robot. So those are the three basic functions that Synth directly allows designers to perform. However, recall that brainstorming is also a large part of bodystorming. So the idea is that Synth should also encourage designers to brainstorm throughout the process of their design session. All right, so we've thus far discussed the interface presented to designers, and now I'm going to talk about our program synthesis algorithm, or in other words, what is under the hood of our interface. Our technical challenge is as follows. Given multiple input demonstrations from designers that vary in length and content, how can we synthesize or construct from the ground up a full automata such that all input traces are accepted or included within the automata? So we set up synthesis as a satisfiability modulo theories, or SMT, problem in first-order logic. I'm not going to go into the math. I encourage you to read the full paper for that. But as I just said, we take a set of traces, and we generalize them to a full automata by maximizing the acceptance of each trace within the automata. In effect, the problem we're trying to solve is an optimization problem, expressed as a max SMT problem. So we formulate this problem within three main constraints. The first is that for a trace with the sequence of human actions, there must be a corresponding path within the automata with the same sequence of human actions. The second constraint is that for a sequence of robot actions within the same trace, the same path within the full automata must also contain that sequence of robot actions. The main reason for splitting up these two constraints is that it allows us to treat circular decision nodes and rectangular robot actions differently. If a sequence of human actions loops back to the same decision node, the sequence of robot actions does not necessarily need to loop back to the same robot action. In effect, splitting the two constraints makes our synthesis problem easier. Secondarily, splitting the constraints allows us to handle error differently within each constraint. In our approach, violating constraint 1 is not allowed at all, while violating constraint 2 is allowed with some error. And finally, the third constraint is that we want there to be only one initial state, and we want all traces to lead to the same sync state. This sync constraint ensures that the end of a trace corresponds to the end of a program. So all of this is performed in real time. The video is not playing. Yep. So all of this is performed in real time. And what you're seeing here is a sped up video of Synth in which each new interaction is computed seconds after designers stop recording new traces and after they stop editing existing traces. All right. So finally, I'm going to discuss how we evaluated Synth. So our goal in our evaluation was to investigate designer experience using our approach to bodystorming human-robot interactions. And secondarily, our goal was to determine the effectiveness of applying bodystorming to human-robot interaction design. Our study design is such that we recruited 12 participant pairs and trained them on how to use Synth. Each pair was instructed to bodystorm either a delivery or an information desk interaction. And they bodystorm this interaction as though it's with a robot. And so one designer would role play as the robot, and another designer would role play as the human. Each pair underwent a 20 to 25-minute design session, and they were allowed to switch off who played the robot and who played the human within these design sessions, within this design session. And after the design session concluded, pairs underwent a retrospective think aloud, in which designers watched the video of themselves bodystorming and retrospectively commented on their thought processes. So our results come in two parts. First, we present the results of the think aloud as an analysis of designers' subjective experience. Second, we present our analysis on designer workflows, in which we look at the order of designer activities within their design sessions. So we ask questions like how often did they act after brainstorming, or how often did they edit after simulating, etc. So I'll talk about the results from the Think Aloud first, which exists within 5 themes, but for brevity I'm only going to talk about 2 of these themes. In the first theme, we found that designers often brought external ideas to their design sessions. For instance, many participants based their designs off of preconceived expectations of how a robot would perform in the scenario being designed for. The bodystorming process implemented through Synth, however, provided ample feedback to designers on their design. For instance, designers often received feedback from their partner or from simulating interactions on the robot. In another theme, we found that designers had mixed experiences with role-playing. Some designers thought that acting was helpful and that it felt natural too. Some designers also thought that it added naturalness to their designs. Other designers felt that the process of acting was artificial and felt unnatural, but designers generally did not think that acting added artificiality to their designs. So now to discuss the results from looking at the design workflows that designers adhered to, we were interested in looking at how much designers incorporated the bodystorming workflow within their design sessions. In doing so, we were interested in how much people used acting or role-playing. We were also interested in how much did they brainstorm. Additionally, simulation is somewhat interesting in that it kind of gets at the idea of environmental similarity, because by simulating, designers are effectively using a prop. So to compute these results, we coded participants' design sessions for brainstorming, editing, acting, and simulating. The figure shown on the screen effectively summarizes these results. Looking at the graph on the left, we can see that over the course of the design session, when participants were actively designing, they spent about 50% of their time brainstorming, 30% of the time editing traces, 10% of the time acting out demonstrations, and about 10% of the time simulating their interactions. This is interesting because it shows that a major component of bodystorming, acting, does not constitute a large part of designers' time. We did see, however, that acting is still a significant part of designers' workflows. The graph on the right depicts which design activities, brainstorming, acting, editing, and simulating, were on average most likely to occur after other design activities. So for instance, the blue arrow from S to B indicates that on average, after simulating an interaction, designers went back to brainstorming 6.5% of the time. So, starting from brainstorming, we can see that designers most frequently began an acting session, and then after acting, they most frequently went back to brainstorming. Therefore, although acting does not take up a large portion of total design time, it is done quite frequently. All right, so to end my talk, I'm going to go over a few important takeaways. First of all, our work is the first to apply program synthesis to the bodystorming design method. Our work culminates in a tool that requires no programming experience whatsoever to create full-blown programs that can run on a real robot, all the while encouraging designers to brainstorm in novel ways. Synth is limited, however, in that only high-level general programs can be created. Low-level editing of these programs is limited. Additionally, usage of synth requires that pre-existing natural language models be used for the classification of designer speech. Lastly, we believe that there is much left to explore in creating more detailed programs. For instance, future work involves investigating the incorporation of real-time components, such as timing between responses. Additionally, design methods other than body storming can be explored in this space as well. We would like to explore some design methods that incorporate more improvisational methods. And with that, thank you for your time. I'll take any questions that you have now, and that is the open source GitHub repository for Synth if you're interested.
All right, so we have a couple minutes for questions. Please raise your hand and we'll get you a microphone.
Thanks. I wonder if you could talk about what kind of conditionals, branches your system supports, and how it knows which way to go down the branches?
Sure, yeah. So transitions in the state machines are labeled with human speech responses. And so at the end of the robot performing an action or a behavior, it will wait for a speech response from the human, and that is how it decides to go down the, to take a path through the interaction. The interaction is completely deterministic as well.
All right. Well, we're getting the next speaker set up. I do have another question. So it seems like this is great for interactions like the ones you showed where I'm physically in the same space as the robot, but often I might want to automate tasks that are dangerous for a person. So I might be at a distance working with the robot.
Right.
Can you say a little bit more about how that might make this more complicated in terms of the design process or how realistic it is to interact and program this way?
Well, I think that as long as we can capture interactions in which safety is critical like that, I don't think it would affect the approach that Synth takes to synthesizing these interactions. I would say that for safety critical interactions like that, I think it would be more important to ensure that the designs that are created adhere to certain model checking properties. You know, in situations where the human might be in a dangerous situation like that, we probably want to make sure with 100% certainty that the interactions that Synth produces would adhere to certain guarantees. That would be the main change, I think.
All right, thanks.